All right. So as we're eating, we'll go ahead and start the next two presentations. The one up here is a presentation by us, my colleagues, Ruby Al-Karbutli, who is a professor at Quinnipiac University, teaching software engineering, and then Srinike Rachuri, who is our mechatronics engineer here at CCAT at the Advanced Design Automation Metrology Lab. So our presentation today is going to be on AI-based digital twin, accounting for production variability. So this is the overview of the agenda for this presentation. We're going to go into model-based definition and digital thread to support AI-based digital twin, example of closed-loop machining for intermittent process control. We'll go through a very simple case study so that you can understand the benefits of model-based production. And I want to set that definition so that it's the precursor for case study number 2, which is a more in-depth and a real-life application of AI-based digital twin for real-time autonomous control. And then we'll talk about the current development on our digital twin software. We'll go into our initial model training results, and then the work in progress on our autonomous manufacturing cell, which is actually a resource for Connecticut-based companies. So I'm excited to present on that at the end. So if we get right into the first section, model-based definition and digital thread to support AI-based digital twin. So the motivation behind this, one of them is the applicable standards. The Department of Defense released a MIL standard 31000 revision B in October 2018 to codify the use of model-based definition as a requirement for technical data packages. So in other words, if you're a supplier of an OEM, such as Pratt & Whitney, Sikorsky, Collins Aerospace, Electric Boat, who are then suppliers to the Department of Defense, you either are already or will be pretty soon seeing these kind of technical data packages that are all digital. And I just want to set the stage as to why it's important to have systems in place at your company to be able to consume this digital data set. The other motivation behind setting yourself up for digital data consumption is the inherent benefits that you get out of it in terms of decreasing time for manufacturing parts, increasing quality, and it goes across the board. So we'll talk about some of those advantages. So really quick, let's calibrate on what we mean by model-based definition. So in this case, we're talking about a 3D CAD model with embedded product and manufacturing information, so PMI. And what the relevance of this is that you go from a traditional 2D data package, which is the 2D drawing, that is human consumable. So a technician and engineer can open up a 2D drawing either on a screen or print it out and have it in front of you, and you're able to interpret that drawing, right? But it's a manual process. You have to take a look at the feature. You look at the nominal value that feature is supposed to be created at. You have the tolerance range within which that feature has to be created at. It's a manual consumption. With model-based definition, it becomes a machine consumable because it's a digital data set. Okay, that's going to be very important as we look at the different processes that are involved in producing a part. So if you look at on the left, that diagram there, if you will, the OEM passes along, several different pieces of data, requirements, product design, and the PMI on the product that they would like produced by the supply base. And those three things get packaged up into a model-based definition data package, and then that gets passed over to the supply base. Now, the supply base, as a company, you'd want to have a system in place that can take that data in and store it, have, your separate business units be able to check that data out, make modifications to it, add to it, check it back in, kind of like a Microsoft Teams, if you will, for engineering data. So a product lifecycle management or product data management system. And what you'll see really quickly is that across the board, you can run analysis on that model. You can run costing, manufacturing, engineering processes. You can plan out your production and generate quality control programs. And it's all kind of contained in that one data set. Again, all digital consumption here. So with that being the case, we can look at some of the inherent benefits you get out of setting up a system like this, where if we take a look at costing, as I mentioned before, there's software from a priori as an example of one of the many softwares that are out there, where you can import a model-based definition file and automatically generate a quote on the part. Now you have to set up parameters, you have to, set the software up, but in essence, it becomes a very quick turnaround on generating a quote that you can get back to your customer. And it's a very detailed quote. It goes through a lot of analysis in terms of, if the part needs machining, sheet metal bending, welding, where it's going to be produced. Is it going to be produced, in one of the states in the US? Is it going to be produced abroad? There's a lot of things that you can set up in the software, which makes it a push button operation in terms of costing. Another benefit is in CNC programming. So you can take the model-based definition that you see on the left side there of the screen and import it into, in this example, we're using SOLIDWORKS CAM that has tolerance-based machining interface. And the dialogues that you see there in the center are the dialogues that you set up. That's your window into teaching the software what strategies to take to machine the part. So what I mean by that is that if you have let's say a hole with a tight tolerance, you might want to choose a different strategy to produce that hole. For example, a spot drilling operation followed by a drilling and then followed by a reaming operation. Whereas if it's a looser tolerance, you might want to use a different strategy, just a drilling operation. And so you set all those up. It's kind of a logic tree. And so when the data actually sees the model-based definition, because it's a digital data set, it pushes it through all of the strategies that you set up, and it's able to automatically generate the NC code. Again, another inherent benefit of having a system set up that can ingest digital data. Another one here is CMM programming. So on the left there, you see the imported MBD file in a piece of software called PCDMIS from Hexagon. In the center there are your strategies that you have to set up in the software. And then on the right is your automatically generated CMM programming code. These softwares across the board, what we see is 50 to 80% time savings in programming your processes. So it's a significant amount. We're talking, once we get to the 80% mark, you're talking about an order of magnitude. Like things that used to take days, take hours, things that, programming that used to take hours now takes minutes. So it's quite significant. Oops. So as an example of one of the benefits of being able to import this kind of data, automatically generating the codes, is that you can set yourself up with what we call intermittent process control. So in this example, we integrated a scanner on a CNC machine, one of the machines that we have here in the Atom Lab side, the additive side, where we have a 3D scanner that goes into the spindle of the machine. So once a part is cut and produced, the scanner can actually pick up the scanner, and it can move the scanner around the part that's just been cut, and we can take scans of the part while it's on the machine. It communicates via OPC UA to the controller. So the machine actually controls the scanner and it triggers the scans. So what you're seeing at the top left is obviously the MBD file that gets imported into Geomagic Control X in this case, that reads that digital format. It automatically generates the inspection report template. And then we can execute the program on the machine through the scanner software. And what ends up happening is We used the program that was generated out of SolidWorks CAM to machine the part. And we can choose to stop it whenever we want. I mean, if we're doing a roughing operation, we can stop after the roughing operation and make sure that we still have enough material to cut away from, that we didn't cut too much. In this case, we did a full machining on this particular part. And once the machining was completed, the scanner was picked up and it scanned the part. And what you see is down at the bottom, it discovered that the width of that last pocket was too big. So it identifies the tool that created that pocket. And given that it knows the deviation, it applies a tool radius offset for that particular tool. And it re-executes that program on the machine so that it basically recuts that pocket back into spec. So again, it's going to go back and now rescan the part and then validate that it, in fact, has brought that dimension into spec. So I call this intermittent because you have to stop the process to get the scanner in there to be able to capture the scans, run the deviation analysis, and then you can continue from there. But what if you run into a scenario where you can't fix it, right? If you cut too much, or for example, you're not going to be able to detect tool breakages right in the middle of machining. So it's a bit of an intermittent way of doing process control. So how do we get to real time? How do we get to detecting, issues that arise, or be able to predict an issue before it arises and make some compensations based on that prediction? Well, this is where model-based production comes in. So we talked about model-based definition. We talked about model-based CNC programming, model-based inspection programming. Now we're going to talk about model-based production. So this is a very simple case study to set the foundation for the next case study that I'll present. And it's really just to get the point across of the relevance of creating a model, a mathematical model of the manufacturing process. So again, here on the left, as I mentioned, we use model-based definition to generate the toolpath. All the way on the right, that's our analysis results that we got out of the inspection software that was that leveraged MBD to create the program. But in the middle, you have your production. You could, even though you're saving time on generating the programs to run the processes, you still may have variability in your production. It's not going to control whether a part is conforming or out of conformance. And so this is where the term model-based production comes from. In our particular case study, we're looking at the DMG LaserTech 65 machine that we use that's over in the back. And we were just looking at recording the spindle power for machining a particular feature on a part. So this was the experiment. We had the stock material shown on the left. That's a 4-inch diameter cylinder, about 5 inches high. You can see the tool path of what we call the feature number 32, which is a circular pocket at the top of the part. So it's a spiral type machining tool path. You can see the end mill that we use is a 1/4-inch flat end mill, and then the resulting part on the right. So again, we're talking about that top pocket where you see the additional drilled holes. And these are the results. What we did was we collected data using a Siemens Edge device. It was connected to the controller, which happens to be a Cinumeric 840D SL controller. So we were able to grab a high frequency stream. So the data collection rate was 500 Hertz. And in fact, we're able to collect up to 100 parameters. In this case, we're only looking at spindle power. And what you're looking at here on the screen at the top left is the inspection result of, we produced 18 parts, and we're looking at part number 3 diameter measurement, which ended up being 1 inch and 856 thousandths. And then part number 12, which had a resulting diameter of 1 and 741 thousandths of an inch. So quite almost 10,000 inch difference in the diameter. And at the bottom left, you're looking at the plot, a cleaned up plot of the power data coming off the spindle for part number 3 and part number 12. So the red line is indicating the power consumed. So it's a time series plot. At the beginning, you're at, obviously 0 power consumption because the spindle's off, and then it turns on. And as you're moving the tool into the workpiece, you see the power consumption go up. And then for example, for part number 3, as the machining is happening, it kind of levels off at 950 watts, whereas part 12 levels off at about 1075 watts. Now, what's interesting here is that obviously from part 3 to part 12, what's happening is because we're using the same tool, that tool is being worn from part 3 through part 12. So by the time we're cutting part 12 pocket, we're doing it with a tool with a dull edge. So what we're seeing here is that in this particular case, in this particular machining operation, that it resulted in the spindle power consumption increasing. Now, the importance of this is making the correlation between the measured value and the data that we're getting off the machine in real time. So what you're seeing on the right is a very simple example of a model that we can use. So here we're just taking 2 points. We know that at a power consumption of 950 watts, we're at a diameter of 1.85 inches. And at a power consumption of 1075, we're at 1.75 inches. And so with those 2 points, we can just, we can calculate a line equation, and that equation there becomes our model from which we can make a prediction of what the feature diameter is going to be given a particular, given the signal that we're getting off of the spindle power measurement. So in this case, if we were to say, well, if we're going to cut apart and we see a signal that's hovering around 1012 watts, we can predict that the diameter is going to be 1.8 inches. So given that we know that prediction, that the feature is going to be off by, by that amount, we can make an appropriate tool radius offset. So because we're getting that data in real time, we can make that adjustment in real time. So obviously the takeaway here is that we don't have to stop the process to take the actual scan. We're taking all the prior measurements that we took on parts that we produced before and calculating this model to then use it after the fact in real time. So this is some, this is a graph that's taken from work that we did with University of Connecticut and Raytheon, actually the work that George had mentioned before as well. What you can see here is that applying this kind of, supervisory control is that you get extended tool life, reduced scrap rate, that equals reduced cost per part and increased production rate. The more the tool wears, the more cost benefit you get out of this supervisory control. That's really the takeaway of this graph. So with that, laying the foundation as to why it's important, what we mean by model-based production, which is creating a mathematical model based on historical data that's correlated with post-inspection results that we can then use to make predictions in real time and then make corrective actions. So now with case study 2, we're getting on to AI-based digital twin for real-time autonomous control. What I talked about in the previous case study was one particular variable. It was the power consumed by the spindle, and it's one particular deviation, which is the diameter deviation of the resulting pocket that was created at the top of the part. In reality, though, there are many different variables that constitute to the cause, and the cause of many different kinds of deviations. And so how do we handle that? And, in this instance, power, we were able to see a percentage increase as the tool wore. But in other operations, for example, if we're doing a drilling operation, it's very highly dependent on the material, it's dependent on actually the size of the motor that's turning that tool through the material. If you have a larger motor, you see less of a percentage difference between the signal change when you're cutting with a sharp tool and you're cutting with a dull tool. So you can't just rely on one signal. And as Dr. Imani had pointed out before, in some of, in his studies, the power signal actually constitute almost nothing to the overall analysis. And so what we want to do is capture all the different sources of variability and as many signals as we can get off of the machine. So here are some of the examples of sources of production variability. It can start from stock deviation. So the size of the stock, basic length, width, height, or if it's a casting forging, you can take a quick 3D scan of it to record the state of the stock material before it goes into the machine. As an example, imagine if you have a casting that has, 50 thousandths more material somewhere. Now, all of a sudden, your machine is cutting more material in that first pass than it was originally thought or originally programmed to do. So your tool wear is going to be more. So that's a source of variability. The hardness of the material. Can you quickly get a hardness measurement? Grain orientation. This is more relevant for like sheet metal bending. Porosity inclusion, again, if you have castings or well, maybe not forgings, but castings more so. The temperature of the stock material, and any bulk stresses within the stock material, that has a big contributing factor to overall warping of the part once it's unfixtured off the machine. Any way that you can get a digital signal on the stock deviation, you want to construct that digital, if you will, a digital twin of the stock material. And then your machine variations, you have programmed spindle speeds. Is your spindle actually hitting that speed? What's the temperature, load, vibration? These can all change. Same thing for your different axes. Are there any overrides that are being applied? Coolant, what's the type, temperature, viscosity of the coolant? And then obviously the biggest contributing factor would be like tooling wear. And then technician distinction. So if there is ability for the technicians to change feeds and speeds on the fly, experience, training preferences also lead to process variability. So what we want to do is we want to capture, like I said, a digital signal across all the different components of producing a part. And if we start with model-based definition, we're already starting off with a digital format. Again, with the stock material, any information you can get, length, width, height, put the values up into a, into a system that captures it digitally. Add an edge device to a CNC machine or connect it via OPC UA to some, cloud software that can extract data. And then post-inspection, right? If you're using a hand measuring tool, does it have a digital readout to a central system? So in this case, an MES system can come in very handy because it has the ability to connect to all these different things, devices, technologies, and software, so that you can aggregate all the data in one location. But if you don't, then you can have separate servers that collect all this data. The important thing here is that we want to aggregate the data and align it in such a way that we can then execute a machine learning operation to generate a model. So what you're seeing here is from the model-based definition, stock material, and edge device data go up into the parameters that are part of the machine learning code. And then the learners, what we call learners, these make the adjustments in the parameters and the model to align the predictions to actual results. Those feed into the machine learning code as well. And once the model is generated, we can consume that model either on the machine or on the edge device for corrective action. And I'll describe what I mean by that. So this was the design of the experiment. we started off with a demo part that we designed. We try to incorporate as many different kinds of features that you would typically find in CNC manufacturing on a 4-inch cube. And then what we did was we created obviously we created a model-based definition file out of it. We assigned a feature ID to each one of the features. And then we produced the manufacturing operations to produce those features. And then a mapping file that maps the manufacturing operation number back to the feature ID. The reason we needed this is because a particular machining operation can produce more than one feature ID. So for example, the top pocket, it's a circular machining path, but we're actually generating a diameter feature ID and a depth feature ID. So the mapping file gets us back to the ultimately to the feature ID. You saw this diagram a little bit earlier from Siemens, from Gus. We used a CityMark Edge device to connect to our 840 DSL control on the DMG machine. And I won't talk too much about this, but the main takeaway from this slide is that we were able to connect into the high frequency data stream. So again, 500 data hertz frequency data capture. This was the actual connection to the machine. So on the Edge device itself, there are 2 Ethernet ports on the back. One's called the X1 port. The other one is the X2 port. The X2 port, you connect an Ethernet cable there on the Edge device. And then on the Siemens 840D SL control, they have a particular port that's assigned to connect for data collection. And that's the X120 port. So it's just an Ethernet connection from the Edge device to the machine. And then we supply 24 volts to the Edge device, and then the X1 port connects to a network. And if that network is connected to the internet or has access to the internet, then we can access MindSphere, and we can download applications from MindSphere onto the Edge device and install the application on the Edge device. Otherwise, if we're just connecting it to the network for the sake of accessing the interface, we access the Edge device interface by bringing up a web browser, typing in the IP address of the Edge device, and then we can get the interface so that we can configure any software that's installed on the Edge device for the purpose of data capture. We did end up using one particular software from MindSphere called Analyze My Workpiece Capture for Analysis. So the Edge device is designed to be able to get the high frequency stream from the machine controller and then process that data on the Edge device. The capture for analysis software, what it allows us to do is actually aggregate and store that data on the internal hard disk on the Edge device so that we can then export it after the fact so we can do our own analysis on that data. What's nice about this piece of this Edge application is that it allows us to select the variables that we want to record. It allows us to define trigger conditions. So when do we want to start the recording? When do we want to end the recording? What triggers the recording event itself? So there's different ways to trigger the recording event. And then obviously we have a way to manage captured jobs and be able to export the data out and so on and so forth. So in our case, what we did was we actually added in the NC code itself, we added trigger phrases as comments to the NC code. So we would put start rec, and then next after that, we would put the manufacturing operation number, and then the particular, well, in this case, we didn't put the feature ID because we had the mapping file. And so what the Edge device does is when you're actually cutting the part and it gets to that line of code, it'll trigger the Edge device to start that recording process. And the stop recording process, we put another trigger phrase in the NC code as stop rec. So when it hits that line of code, it'll stop the recording process. The nice thing about the way in which we're doing this is that we then are segmenting out the signal per manufacturing operation. So in other words, for manufacturing operation 10, let's say, if we're going to produce 20 parts, 100 parts, in that particular folder in the Edge device, we have a folder for manufacturing operation 10, and we're going to have as many different, data collections for the number of parts that we ran. So the data is already segmented, and we don't have to go in and do that via code. So here are the results of doing the data recording. Again, this is on producing 18 parts. So relatively small data set. At the top left, what you're seeing is feature number 10, signals. We're only showing the power consumed by the spindle. We captured 92 parameters in total. And they constitute, power consumption, torque, velocity feed forward, a lot of different parameters for each of the 6 axes or 6 motors on the machine. So X, Y, Z axes, and then you have A and C because it's a 5-axis machine, and then you have your spindle. So what you're seeing here is obviously the signals aren't right on top of each other. There's variability. In fact, there's a range of power consumed from 825 to 975 watts. So that's 18% of variability there across the 18 parts. If you look at the graph at the bottom left, you're looking at feature number 8. This has a variability of 17.6%. The graph at the top right, 158%. That's a bit much because this was a drilling operation, and there was some chip compacting on one of the parts. So you see the spikes go up in the graph, which is what's constituting but if we zoomed in on just a small area, that's about I think it was 19%. And then feature number 2, we're seeing 25%. So it's significant. It's not 1 or 2%. It's, we're talking about, above 15% variability. So how does this relate to post-inspection? So we used a couple different machines to do post-inspection on the parts. The reason we did this was because we wanted to see how the accuracy of the post-inspection equipment affects the prediction accuracy from the model. So do we always have to use an extremely high accuracy machine to get high prediction accuracy? Because the two aren't exactly related. So we use the GOM ATOS, which you see on the right, on my right. We used an M3DI scanner. Both of those are structure light scanners. And then we also use the CMM, and then a comparator that uses the data from the CMM. So here's the results on the post production inspection data. Basically, the takeaway on here is that you see that, for example, for feature number 1, the graph on the right, there's variability. It's not a straight line. And then on the bottom there, you see for feature number 8, the slot height and slot width. Again, you see variability. So we clearly see that the features aren't produced at the same dimension across the 18 parts. And we also see that there's variability in the signal. So this sets the basis for wanting to use machine learning to process that data. As we heard before, machine learning does a lot of things automatically, if you will, inside of a black box. So we don't have to necessarily be concerned about the specifics if we're looking at it from, generating an algorithm that is more logic-based or statistical-based. So some of the factors are, if we're capturing more than one signal, how do we weight what signal is contributing more to the deviation than others? In other words, is the power signal contributing more than the torque, right? Is it the axis deviation that's contributing more? And it's dependent on the type of machining operation. If I'm doing a circular pocket, I'm using my X, Y, and Z axis. If I'm doing a drilling operation, I'm only using my Z axis, right? So the different types of manufacturing operations will mean that you have different weights for the contributing factors of the deviation from the 92 parameters that we're capturing off the machine. I'm going to invite my colleague, Ruby, to come and talk about the digital twin software architecture that we're developing. This is a diagram to kind of walk you through the logic behind how we're setting this up.
Thank you, Nasir. All right, so Nasir set the stage. Most important part, I think the biggest part and most of the work is collection of the data, correct collection of the data, and then us as computing, using the computing power to format the data correctly for the machine models. So you can see here, the black box or the box in the middle is usually your software. On the left and the right are inputs, and then the main outputs that we get are here. So you can see that we're getting the initial machine signals coming from the edge device are streamed from the machine to the edge device. We have the mapping file with the initial specifications. We have our post-inspection data here. And we have also some information or the per part inspection file. So you can also see where these come from, the different softwares, some of the different softwares. Now, the work that we do is, or half of the work we do is basically converting, cleaning, getting rid of the noise in the data, making sure that we're formatting the data in a way that the machine learning models can digest or can run with. We get all of this information and we put it in a concise format for the machine learning algorithms. We run a number of different machine learning algorithms. This is very necessary for the correction of the prediction and for the choice of which algorithm to run. These are all typical machine learning models. We're using Python. We're using Python machine learning libraries, ready existing libraries. So we have ran the support vertical support vectors, random forests, Bayesian network, and so on. I think CCAT will go over most of these. But most importantly, I want to show or take a look at from a user perspective, what is your inputs and what's your outputs. From a user perspective, you input or you put all of these different data parts into one single directory. And you choose your machine learning model one at a time so you can run it. So that's a user, very basic user. And what you get are two things. You get some user display telling you the classification and telling you the results of the prediction. But also, and that's the key file that we're looking for, we get the model that's gonna further run at real time on the machine. So all of this work happens maybe, let's say, once every couple of months, once every 2-3 months with the collected data just to update this file. And then during runtime, this is the file that you basically get. All right, Nasir, do you want to take this one?
So what we're doing is this is Ruby talked about the overall architecture. This is the interface. So our scanner software is inherently a digital twin software because you can put a part in front of it, scan it, and then you have a digital replica of that physical part. But now what we're doing is adding capabilities of digitizing the process. So you have the CAD model, the PMI, the 3D scan data. And so because you have those, you can extract the measurements. And now with the real-time data that we're getting off the machine in the same coordinate system as all of those other data sets, we're in a situation where the software can now automatically pick out, or I want to use the word segment, the data and adjust or self-correct once a trained model is deemed to be let me say it a different way. So in the interface, once we have all the data collected, we have a model, we've executed that model on the machine. We're in a situation where in the software, we can predict what the feature accuracies are going to be. And then we have the ability to scan the part on the machine and actually extract what the measured values are and compare those to our predictions. And in that way, because we're in the same workspace, we can correct for any deviations between the actual measured value and the predicted predicted value. So the machine learning code is kind of wrapped up into one dialogue. On this dialogue, what you do is you select the directory where all the machine signals are stored. So this is once you do the data collection on a number of part runs, in our case, it was 18. You export out that data from the edge device into a directory, and then you specify where that directory is, the location of it here in the software interface. And then you select the inspection reports for each of the parts, where all the inspection reports are stored. It's a directory location. And then you specify the mapping file. And then you hit run. And then it basically, the software in the background will calculate, run the machine learning codes, calculate a model for the machine, and output that model that we can then take in and consume on the edge device for corrective action. So what I'll do now is I'm going to have Srinikit come up and talk about our initial model training results.
All right, so first, let's define what our experimental procedure would be. So we cut down the number of signals from 92 to a list of more relevant signals. And basically, then we scored each of the residual values from the nominal in two different ways. So we did two different splits. So we did an even split, which splits the Z distribution up evenly. So each section, a low, average, and high residual, contains 33% of the data. And then we also did a normal distribution split where it's 68% in the middle and then 16% on the two fringes. This is just to see how robust it would be in the in the chance that you wanted to change how the data was being classified. So we tried quite a few machine learning models. This is using scikit-learn in Python. And we did a neural network with a classification. So that means we used the z-scores mentioned previously. And it was able to hit very reasonable accuracy measures with a reasonable training time of 10 minutes. In the bottom left, you can see the residual values for each of the parts. And in the bottom right, you can see the reds are the predicted, and wherever you don't see a red dot overlapping on the blue dot, that's where the prediction was wrong. So you can see that in this small subset of the data, it's pretty accurate and usually gets the prediction correct. And these are our overall results. So we tried all of these different algorithms. So that's random forest classifiers. That's a neural network. That's a k-fold neural network. There's logistic regression, and there's a Bayesian algorithm, and then there's support vector machines. So you can see that some of them were not ideal for this situation, especially the bottom three. They do better with different types of data. The sheer amount of data that we're receiving kind of makes those algorithms not worth using. And the support vector machine in particular took almost 2 days to compile. So there's also that to keep in mind. And then we also, instead of just classifying, we also tried to do a regression model, which instead of classifying the data into z-scores, basically a low, high, or medium residual, instead it would try to actually just estimate the residual value of each of the features. So for example, if a diameter was supposed to be, let's say, 10 centimeters, and the actual result was 10.1 centimeters, then the residual will be 0.1 centimeters. And so it would try to estimate the residuals based off of the input data from the machine signals. So the this type of estimation is something that is more computational heavy. So we only ran it with a couple algorithms that would actually work. The random forest regressor was actually quite accurate and trained within 5 minutes. But it did have the issue where I think it is overfitting because of the just how accurate it's able to do it in such a short amount of time. And when you do test it again, you can see that running it on the same data set will just continuously give you a high result. But when we do get another data set to test with this, it will be interesting to see if the same model that we generated with this data set is able to retain that level of accuracy with another data set. The the K neural network and the other regressors didn't really hit the mark with the type of accuracy you would need in a machine scenario.
Thanks. So the next steps that we have here are obviously we're generating the model. We want to be able to consume that model for corrective action. So we have to go through a failure modes analysis. So what's causing the inaccuracy? Corrective action algorithm. So what do we control on the machine? We're looking at 3 variables: the tool radius offset, the speed override, and the feed override. So what percentage of one of those 3 variables do we adjust? And then we've got to develop the edge device software so that we can consume the model on the edge device, establish a high frequency communication with the machine controller, establish a high frequency machine controller parameter adjustment, and then manufacturing process simulation using digital twin. So in our software, we want to be able to use the model and run a empty code and then produce a model of a cut part and then be able to measure that model that has the predicted values that part's going to come out to given the current state of the machine. And then compare that digital twin with actual measured value, as I mentioned before, so that we can make adjustments to the model based off that deviation that we might see. So the next one, I know we're over time here, so I'm going to just rush through this. This next part is it's a resource for Connecticut manufacturers. We're setting up an autonomous manufacturing work cell actually right here. You can kind of see the preliminary layout of it. We're going to have a CNC machine with a CNumeric 1 control. We have a number of collaborative robots. So this cell is intended to be a cell that produces parts continuously without any human intervention. In other words, if a tool starts to dull, if a tool breaks, if there's any any sources of issues that arise during the manufacturing process, the system will be able to detect and account for it on its own. So the overall architecture here is we're going to have a PLM system, MES system that's going to be collecting all the data from the machines. And then above that, we're going to have an overarching AI ML system that's going to be importing or streaming data from the MES and PLM system into it, so we can generate a model and continuously retrain that model, periodically, to then apply, if you look at the bottom, to the autonomous control corrective action that feeds into the CNC machine and each of the robot cells and the inspection equipment. So again, we're gonna go through constructing the system, both hardware side, the connections that we need to make, the softwares that we have to have in place, the software that we're developing. And what's key is the software that we're making it generic so we can test any machine learning algorithm. So we're gonna want to put we're gonna want to test Professor Imani's algorithm and any other algorithms that are produced in the future through this system, so that we can validate that the technology is of benefit to manufacturing. If out of this as well, we're going to be documenting the process of constructing this, and we're going to be generating a playbook, if you will. So if you're wanting to do this at your facilities as well, we're going to have a kind of a guiding book for you to use to construct a system like this. We're also going to be holding a lot of technology demonstration workshops around this cell. What you're seeing here is just high level. We're going to be incorporating a lot of different sensors. You heard about the Bomber smart cameras, the edge devices from Siemens, the software development that's being done at University of Connecticut and Raytheon Technology Research Center. And we're going to want to we're going to hold regularly scheduled demonstration workshops for companies to come and understand how all this is working and the results that we're getting out of it. And what's nice is if you have a particular process that you'd like to test this system with, this is what this will be here for. So you could bring us your parts, we can produce your parts, and we can see how the system works on your particular parts. And then we can support ultimately with technology adoption. So the whole purpose of us creating anything here in the lab is to lift and shift it over to your manufacturing companies so that you can adopt it and take benefit of the technology. So look for our announcements. It'll be exciting next couple of months as we develop this system, and hopefully we can see you back here to actually witness the system running. You're going to hear from some of my colleagues about some of the funding opportunities that you have as Connecticut businesses to subsidize the cost of onboarding some of these advanced technologies.